Big data is often associated with networks, and such networks tend to be complex. Although big data is massive and messy, it does have a structure. Now, last week we looked at the question, what is big data? We saw the 3 V's, high volume, high variety, and high velocity. We also saw that big data is cursed. High velocity means that we need to be able to analyze results quickly, or that we need algorithms that run in a reasonable amount of time. It's interesting to note the first weather forecast required more than 24 hours to be calculated. The important term here is complex. Complex tends to mean there is a high-dimensional underlying structure to the data. The underlying structure is what allows us to often design faster algorithms. The main example for this lecture is going to be what's called the SubEconomy problem. A SubEconomy is a subset of households that rely on a common set of businesses. They don't shop at other businesses, they all shop at the same businesses. The data here is each household's monthly transactions with each business. Notice that there's no e-commerce. Household 1 in this example works at business 4, spends money at businesses 1 and 3. And a SubEconomy would be a set of households that only shop at the same businesses. So this is not a strict SubEconomy problem because it's not closed under businesses, only under households. You see we have a SubEconomy because households 1, 4, and 5 do not interact with business 2, only with businesses 1, 3, and 4. So how do we find a SubEconomy? Well, all we have to do is check subsets of households to see if they have zeros for the same businesses. And then the largest subset found by this approach will be the largest SubEconomy, i.e. the answer to our problem. For example, let's suppose we have a town with 250 households, that's about 700 people, and about 20 businesses. To find the largest SubEconomy, we just use the direct approach. Now, let's suppose we did this on the Titan supercomputer in Oak Ridge, Tennessee. If we did, there are 2 to the 250 subsets that we have to check. That's a huge number of subsets. And it's going to require 5.73 times 10 to the 52 years on the fastest computer in the country. So clearly the direct approach is not the approach we want to take. And certainly this isn't that hard of a problem, because in a town of 700 we could probably figure out the SubEconomies just by knowing each other. And in particular, that's what we're going to do. So finding the largest SubEconomy, the direct approach is too slow because the direct approach is actually equivalent to the subset sum problem. But the direct approach ignores the structure of the data. So instead we're going to use graph theory. In order to use graph theory, we're going to have each household as a node or vertex. So Smith, Johnson, Williams, Jones, Brown, Davis, Miller, they're going to be used to label a set of nodes or vertices. Now here's the definition of a simple graph, a set V called vertices along with a collection E of 2-element subsets of V. No vertex is paired with itself, no edge occurs more than once. So for example, here are some edges in our SubEconomy graph that we're going to construct. We're going to use criteria functions. A criteria function is something that takes 2 pairs of observations and returns true or false. True means there should be an edge between the 2, and false means there should not be an edge. There are many, many possible such criteria functions, and one of the things we'll want to do is choose our criteria function wisely. Now, if we're given a rectangular data set, a box of rectangles, then the way we construct a graph is we make the observations into vertices. Just note, we could have used features as the vertices, and there are times when you want to do that. Then we define a criteria function between 2 observations that defines when they're close or similar. And then we place an edge between those if the criteria function is true. So in our subeconomy problem, our criteria function is going to return true if x and y, the pair, is a subeconomy. Otherwise, k of xy will be false. Notice this means we're going to be checking pairs of households, not subsets. So for instance, this first pair, Smith and Johnson, clearly it's not a subeconomy. K of xy is false. On the other hand, Johnson and Brown do form a subeconomy, as you can see by the common set of zeros, so K of xy is true. Williams and Miller also form a subeconomy, again a common set of zeros. And Brown and Davis, they form a subeconomy. And so here we have pairs of households that form subeconomies. Now using this information, we can place edges between households using our criteria function. So if k of xy is true, as it is for Johnson and Brown, we put an edge. If k of xy is false, as it is for Smith and Johnson, then we have no edge there. Williams and Miller, they form a subeconomy, the pair of them. They shop at the same businesses and avoid the same businesses. Brown and Davis, again a subeconomy. Johnson and Davis, once again, that's a subeconomy. And so now we have our subeconomy graph showing what we did earlier, the relationship of pairs of households. The largest subeconomy, therefore, is the largest connected component of the subeconomy graph. So of all the vertices, the largest set of vertices that are connected to each other, that's the answer to our problem. Now there are 250 times 249 over 2. There's 31,000 matchings to compute. And the key here is that you can actually do this very easily with just a single processor. We can actually find the largest component in linear time. Let's look at an example of using the IPython notebook. This is actually from your assignment. I'm not going to try to narrate it. You'll be doing the assignment and all the text there explains what's going on. You will notice that the assignments are going to be keyed on your username, so each of you will have your own unique assignment each week. So feel free to discuss things with each other because you're all going to be doing something different. So this is our data. We saw this briefly in the notebook. We want to talk about households. Right now, like a spreadsheet, the data is going to be given to us in terms of businesses as the column headings, and transposing that will make it in terms of households. We're just looking at some examples for the Smith family, and notice that there are some falses in there. So the Smith family and the Johnson family don't all shop at the same businesses and avoid the same businesses, so they don't form a subeconomy. So we define this simple little procedure, the is subeconomy procedure, and Smith and Johnson don't form a subeconomy. Now, of course, there's 250 households. You can see the names there of the households. And most of the time, when we choose a pair, we're not going to get a subeconomy. So we can create a graph from a criteria function using is subeconomy, and we apply the graph. We find the set of largest components, and we notice that we have a component of size 8. What we see is we have a lot of subeconomies. So let's draw the graph. And well, that's a mess. And well, it doesn't help to draw it circular. So let's do something else. Let's take our subeconomy problem and let's actually find the connected components And we're going to find the connected components of our subeconomy graph. There's 8 of these. And so these are the subeconomies. So let's look at the 0th. That's the one of size 8. So this is our largest subeconomy. And there you see it. Duncan, Thompson, Ellis, so on and so forth. Here's the next smallest. And here's one of size 4. Notice all the subeconomies are completely connected. That means that they're what are called cliques. We'll actually look at that later. So this is the result. And this is not atypical. Big data is not pristine. It's not unusual that you don't get initially the satisfying answer you wanted. It's messy. So we didn't get one large subeconomy like we would have hoped maybe was in this data set. We get lots and lots of little subeconomies. That may be misleading, as we'll see later. Also, it's not unusual to use graph theory to represent data sets. And often graph theory is better than other things. In general, however, we use more than one criteria function. So notice we're going back. Here's big data as a graph. And our vertices, the observations. Now we choose criteria functions. Not just one, but several. So here's the first criteria function gives us these edges. The second gives us some more edges. In theory, all the information in the data set could be encoded into a graph. But in practice, we don't. We'll be using graph theory in this course from everything from simple illustrations to the basis of our algorithms and predictions.